Hello, this is a continuation of the statistical process control notes for continuous improvement, and this is really going to build on what we just discussed in part 1. So I'm going to go ahead to slideshow. And in part 1 we talked about SPC and its basics, and we focused on the so-called X-bar and R charts. So remember, the X-bar and R, or X-bar and S charts, are used to track the average of rational subgroups over time. But in this section, we're going to talk about a couple of other types of charts. One is called the individuals charts, and we use this when it's not possible to subgroup. In other words, rational subgroups aren't possible. And then I'm going to introduce something called the exponentially weighted moving average chart that is very useful for tracking shifts or patterns over time. Much more sensitive than the standard Shewhart charts. And then I'm going to talk a little bit about control charts for proportions, and I'm actually only going to focus on something called a P chart. Okay, and on slide 4 is just a little diagram to help you understand charts, and we're going to talk about IR charts, individuals charts, and EWMAs, and then briefly about P charts. Okay. So again, the idea of an individuals chart is at each time period you can only get a single measurement. So when you construct the chart, all you can plot is an individual. So on slide 6, I thought you might find this interesting. These are individual times for the winning men and women in the Boston Marathon from '72 to 2014. And you'll notice for the men, more or less since around 1980, it's been pretty stable. Now, I think somebody broke the record last year. And it does appear there was a shift. I've been told it has something to do with the changed the course of the race at one time. I don't really know. But then look at the women. Particularly look at until around 1982. A large downward trend. And I've been told the explanation for this is women have run in this race for decades and decades, but it wasn't until '72 that the times were counted and it became an official marathon. So most women who were really very competitive marathoners didn't run in the race. There was no point. And once they started collecting times, eventually their times came down, and you can see also since the early part of the 80s their times have been pretty stable. Okay. So it is kind of interesting, and I just show this for an example, but it is a case where we are tracking individual measurements. We'll talk about how to construct the chart. The problem with individuals charts are there's no rational subgroup. I get one measurement at each time period, so how do I calculate the range or the standard deviation? I've only got one measurement. The answer, it's imperfect, but it's the only one we have, is called the moving range. We assume points on the chart next to each other are more alike than points that are farther apart. So we have to make the assumption that the moving range, the range of two consecutive points, is common cause only. Okay, it's a difficult assumption sometimes to buy, but in general the process seems to work. And usually when you construct these charts, if there are gross violations of the assumption, you'll see them when you make the chart, and you can eliminate points that appear to be out of control. So we're going to plot the individual measurements, and we're going to plot moving ranges of successive points. Okay. So basically what I'm going to do is just go ahead and show you some examples. So I'm on slide 10. And this is data called production costs. So each week this company tracks its weekly production costs, and there's no way to really subgroup the data. Each week you get one measurement, so we'll do an individuals chart. Okay. I did mention the chart does make an assumption of a normal distribution. Therefore, it's typically a good idea to plot the data on a normal quantile plot to see if it's approximately normal. Overall it is. We have one point here which turns out it's related to a short production week, and I don't remember if it was weather or holidays, but in general it plots in a straight line, so we assume it's normal. Okay, so where do we do individuals charts? Well, again, we can do control chart builder, or we can do the control chart menu itself. Okay, so why don't I again just go over to jump and we'll take a look at the data. Okay, if we can find jump here, there we go. Okay, so for jump, I'll just open up the data file. Production costs. Production costs 2 is the actual file we're using. Okay. So we go to Analyze, Quality and Process, Control Chart Builder. So week is our subgroup variable, and costs, the weekly variable. And notice again, Control Chart Builder looks at the type of data you have and then decides upon the chart. So it creates the shoe heart chart for you. And then let's go to Analyze, Quality and Process, down to the Control Chart menu, and IR chart, Individuals, Moving Range. So week is the sample label, cost is the process. Okay. And I'll just show you while I'm in here, if you are interested in the Western Electric rules, in the report menu for the control chart, okay, click on the menu, come down to show zones. If you want, I'll go shade zones. These are these 1 sigma zones that we talked about. Okay. In fact, that may be too difficult for you to see, so I'm going to take it off and just show zones. Okay, so there are the zones, and you just pick the tests, whichever ones you happen to want. Okay, so they have tests. I'll say just do them all. And up here, notice we have a point out of control at time period 3, and then we have some other points plotting out of control. And by the way, they're out of control because there's clearly an upward trend. So you can implement these rules, and Jump Help has a reference to the rules if you're not sure exactly what they are. And that's the basic idea of individual and moving range chart. And the average down here, okay, I'm pointing to, the average moving range is then converted to a standard deviation that is used to construct the 3 sigma control limits. This chart plots individual measurements, not averages, so the control limits are plus or minus 3 standard deviations, not 3 standard errors. Okay, so that's basically the idea of the individuals chart. And if you're interested in the normal quantile plot, just as a review, you would go to Analyze, okay, Distribution, and Costs is the column of interest. And then in the Report menu, you would select Normal Quantile Plot. Okay, so I'm going to go back to the notes. Now, exponentially weighted moving average charts, I'm not going to go into a lot of depth about them. What they're based on is the fact that when we use a Shewhart chart, each point is used by itself to judge the state of control of the process. We say there's no memory in the chart. In other words, that single measurement has no idea of where the process has been in the past. But typically in these control charts, we find having past information or some memory can be a good thing. In other words, where the process has been also gives you information about where it is at present. So basically this is a concept in engineering, process control, where they don't just use the most recent measurement, they also use historical information about where the process has been and where it might be going. So EWMAs take averages over time. That's how they work. So when you plot an EWMA chart, okay, where did that go? There we go. Let me set up a pen. Okay. X bar, not X bar, but X sub t is what I meant to say, is the current measurement. Lambda is a weight, and it's somewhere between 0 and 1. And then notice this, what else is plotted, this z sub t minus 1. That's the weighted average from the previous time period. And we can show that that second term, that z at t minus 1, incorporates information for all the past observations. So it's a weighted average, and lambda is the weight, and typically it's set at 0.2. So each time period we don't plot a raw data point, we plot an average. So lambda is a weight, usually it's 0.2 or 20%, and then the other is 1 minus lambda. So typically 20% of what's plotted is the current measurement and 80% an average of the past. Okay. And as I said, based on years of simulation studies, to get these to work well as control charts, lambda is typically set at 0.2. Okay. This next chart on 17, I won't get into. It just shows you that z t minus 1 can be shown mathematically. It incorporates an average of all past observations. And what's interesting is, as you go back in time, the weights die off rapidly. In other words, even though theoretically we're incorporating all past information, the weights assigned to past observations die out to 0 very quickly. In fact, we say they die out exponentially. Okay. A couple of things to be concerned with. Since this chart is an average, if something happens very abruptly, an abrupt shift, these charts can be a little slow to react because they're averaging that abrupt shift in with past data. So EWMAs are really good at catching small shifts and slow trends and cycles. They're not so good at big sudden shifts, so often EWMAs are used in conjunction with standard Shewhart charts. And remember, for a shift of 1.5 sigma or larger in the mean, Shewhart charts are actually quite sensitive. So EWMAs and Shewhart charts complement each other. In fact, the EWMA really removes a requirement for the Western electric rules. So if you use an EWMA and a Shewhart, you really don't need to be using those Western electric rules. So let's start with the pistons data, and I'm going to go back to jump and close that. In fact, we'll just use the pistons data. And I'm going to go to Analyze, Quality and Process, and I think I'll just go to Control Chart. You can do these in Control Chart Builder or in Control Chart. I'll pick EWMA. Okay. So hour is the label and diameter is the process. And the weight by default is 0.2. There's really not much reason to change that unless you're just simply exploring the data and you want to try different weights. Okay. So take a look at this chart, and I'm going to combine that. I'm going to go back and generate an X-bar chart just so you can see the two side by side. Okay. So hour, diameter, and I'm actually not going to do an S chart. Okay. I'm going to plot these two charts next to each other. Okay. So if you take a look on the left and the right, notice on the right, okay, that although eventually we do pick up some issues, notice in the EWMA how quickly we pick up on that out of control point at time period 13. But even more, take a look at this trend. It just jumps out at you where it's really hard to see in the X bar chart. The reason is the averaging is smoothing out the data over time. It's reducing noise and making it easier to see. Likewise, starting at about time period 30, you can see this process is taking an upward shift, and in fact, well before it went out of control, somebody most likely would have intervened. I like to tell people you shouldn't think of control charts simply as something is either outside of the control limits or within the control limits. And the reason is, you know, these trends do occur. The EWMA picks them up quickly. Shewhart charts do not. But think about driving your car on the road and the sides of the road are the control limits. If you use the Shewhart approach, if the car were heading off the road, you wouldn't do anything until you were off the road and you may hit something. So basically, in using these control charts, the EWMA concept says, no, you really should react long before you head off the road. And of course, drivers with some experience can quickly, and they unconsciously even, just keep making adjustments. Well, that same thing happens with control charts. When people get used to looking at them, they can typically very quickly pick up on when a trend is occurring. So you can see the power in the EWMA to detect these trends and shifts when they occur. Okay. So again, I'm going to go back to the notes, and I walk you through the EWMA, so we've already done that. Okay. And then I'm going to show you another individual's chart, and this is from a continuous improvement project at a Boston hospital. And what they do, they have an emergency neonatal care unit, and they service other hospitals. This is a unique service. Many hospitals don't have it. And what they were doing is tracking the time delay between getting a request from service from another hospital and the time it took to leave the hospital. And what we'll show you is what an individual's chart looks like for the 70 consecutive requests. There is no obvious way to subgroup the data, so this is an individual's chart. Okay. And we do the normal quantile plot. It actually doesn't look like it's quite normally distributed, although it's not an extreme violation. But because of that, I won't literally interpret the control limits on the individual's chart. It still is useful to use. I'm just not going to react quickly if something goes outside of the control limits. So again, we can go to EWMA or IR chart. So here's the EWMA. And frankly, in this chart, you can see there appeared to have been a number of shifts. In fact, maybe as many as 3 of them, if you take a look at it. So again, what I think I'll do is just go over to jump, and we'll open up the data. I don't need that data right now. So we'll look for the OB trends data. Okay. So again, I'm going to go to quality and process. Again, you can use control chart builder if you want to, or you can use control chart, either one. So I'll just use control chart, and I'll do the EWMA. So the sequence is the sample label, not the process, in minutes, and I'm not going to worry about where we set the control limits, given this is not an in-control process. But you can see on this chart, they do appear like there may be 3 distinct shifts, which may indicate that people have been working on the process. Also notice the average time is 57 minutes, almost an hour to leave the hospital. So let's go back, since we're plotting weighted averages here. For comparison, let's go back and plot an individual's chart. Okay. So this is sequence, minutes, process. Okay. And just compare the two. We can do that quite easily here. And notice all of the noise in the individual's chart, making it very hard to see these subtle patterns. But when you look at the EWMA, you can see there have been some shifts, maybe even a downward trend, which could indicate that people are working on response time. But look on the individual's chart. I mean, look at the variation that occurs. For instance, time period 23, it took them almost 110 minutes to leave. Okay, I mean, that's a long time for emergency care. And that's all they're measuring, by the way, is time to leave, because they have no control over what happens once you leave. But looking at the chart, you can see a couple of things. One, it looks like a downward trend, but also notice that it looks like the variation is shifted, and at least they're getting a little more consistent. Okay, so that's an example, what I would call a transactional Six Sigma example of the use of an individual's chart. Okay, and also phases we need to talk about. It turns out when you're doing improvement projects, at some points in the project you may make changes. And when you implement changes, if you have some sort of grouping variable that identify the changes, you can actually use those to create what are called phase control charts. And I'm going to illustrate this with another version of that neonatal care data, where in this case we'll say up until time 40, okay, time the 40th sequence, they were running at one process, and then they implemented an improvement. Okay, so again, it's easiest to just go over to Jump and illustrate this to you. Okay, so I'm going to open up another version of this data. Okay, this is called, where is it here? Six Sigma data set OB Trans 2. Okay, so notice this has a column called change, and it has 2 levels. There can be more, called before and after. So what I'm going to do, again, I'll go to Analyze, Quality and Process, and I'll go to Control Chart Builder. Now, with phase control charts, you cannot use an EWMA. The reason being, EWMAs average over time, and there's no simple way to stop them abruptly from averaging and restarting. Okay, so the response sequence is the label, minutes is the response. Okay, so Jump immediately knows it's an individual's chart. And then where it says phase, I'll put phase. So notice this is a nice way to demonstrate improvement. So if you look carefully, okay, they have reduced the overall time, okay, from about 60 minutes to 52. Okay, not great, but they've also reduced the variation. You can see it right in the control limits. So sometimes these phase control charts are a nice way to track KPIs in a project because it's a nice way to show if you've actually made improvements. So phase control charts are very useful and very helpful, especially for plotting KPIs. Okay. So I'm going to, and I just wanted to point something out to you. These often you use words for the phases. And they may not plot correctly because they go in alphabetical order. For your column containing the change variable, go to the column info window, look under column properties and something called value ordering. And that will allow you to order how you want the levels of that alphanumeric variable to plot. So often with these phase variables, since people use words, you will need to go into value ordering and set the correct ordering to get the phases in the correct positions. Okay. And one last chart I want to talk about is called a P chart. And a P chart is designed to track defectives. These could be defective parts or bad service, and either in this chart something is either defective or it is not. The service is either good or it's not. And this is different from what we call a defect. A defective means it wasn't acceptable to the customer. They couldn't use it, or they really didn't want it, sent it back, whatever. A defect, on the other hand, is something that's, well, not perfect. The product is still useful. Okay, so a defect could be something like serving food to somebody in a restaurant and they said it's too cold, you take it back and reheat it. Okay, if it were defective, they'd tell you this is completely unacceptable and you'd have to throw it away. And a defective part would simply be something that doesn't work. But a part can have defects and still work. So I'm making a distinction between defective and defect. So basically for a P chart, what we track over time is the proportion of defectives. And I won't get into a lot of detail, but this is based on what's called a binomial distribution, and that's a distribution which has only two levels. Typically success or failure, defective, non-defective. Okay, so the P chart is, the theory behind it is based on this distribution, but I'm not going to get deeply into it, and I'm just going to get right to the point. Okay, so here's an example. This is a manufacturer. They make these electric motors, and they do them in lots, and a motor either works or it doesn't. So for some last set of production runs, they've actually tracked the proportion of the motors that didn't work. Okay. So once again, I'll just go to jump, and we'll open up the data set P chart. Okay, so there is P chart. Again, I go to Analyze, Quality and Process, Control Chart, and I'm going to select P chart. So I'm going to put hour as the sample label. Wait a minute, that grabbed the wrong data for some reason. What is going on? There, let's try it again. Quality and Process, Control Chart, P chart. Okay, so subgroup is the sample size. That's the number of parts per lot. Defectives is the process. And sample number is the label. That's all you need to know. And there's the chart. And by the way, you'll notice the control limits are not constant. They look like the skyline of a city. That's because the width of the control limits is a function of the sample size, and the lot sizes differ. So these are correct limits. They go in and out because of the varying lot size. And frankly, the process looks to be in control, and it's running at about 20% defective. But they're consistent is what that says. Whether you like 20% is another question, but you're consistent in running at 20%. Okay? So pretty simple to create a P chart. Okay, so again, I go back to the notes. Okay. And you use P charts in many different ways. Here's an example. This is proportion of expedited shipments, which can cost a company a great deal of money. So these are weekly proportion expedited. Notice a lot of points appear to be out of control. You have to be careful because there are rigid assumptions about these charts. One of them being that all the sources of the lots or the data you're putting in here have the same underlying proportion defective. Well, it turns out in this case they don't. This data is being aggregated from a number of distribution centers, and they all naturally run at different levels of proportion expedited. So how do we combine the data? The answer is calculate your own proportion and then use an IR chart. Okay? So here I calculate a proportion, and there's an IR chart, and you can see the process is in control. Okay? The rest of these charts I'm not going to talk about. You can read them. They aren't used much in quality, especially transactional, but you can read about them. And again, I'm